Okay, in this video I'm going to do a trigonometric substitution problem. I've got a couple of these on my website, so this shouldn't be the first one. So I'm not going to write down all the formulas in this one. In this one we're going to integrate the square root of 9x squared plus 4. And again, you're going to do trigonometric substitutions when you see basically square roots, quadratic equations, quadratic expression under square roots is going to be a good time. It says if you have a variable squared plus a number squared, the substitution you use is x equals the number tangent theta. Well, that's not quite what we have here, but I can rewrite 9x squared as 3x quantity squared, right? That'll still give me my 9x squared if I square both parts, plus 2 squared. So here it says we use x equals a tangent theta. Here my substitution is going to be 3x equals 2 tangent theta. Okay, so that'll be my initial substitution to help me get going here. Notice if we calculate this, we get x equals 2 over 3 tangent theta, just by dividing both sides by 3. Take dx, we'll get 2/3, the derivative of tangent is secant squared theta d theta. Okay, so I'm going to plug this stuff into my integral over here on the right hand, or excuse me, on the left. So I'm going to plug all of this stuff in. Okay, so it says dx is equivalent to 2/3, all divided by the square root. You know, think about again 9x quantity squared being written as 3x quantity squared, and we said that 3x is 2 tangent theta squared, and then I still have my plus 4. I think I was going to put my secant squared over there, but I'll go ahead and just put it on top. So dx, got too many dx's up here. Dx is just 2/3 secant squared theta d theta. Okay, so again, I'm picking my substitution, and then basically just calculating your dx from that, and then plugging that into your integral. Okay, so at this point, what you have to do is basically just keep simplifying down your integral. So I'm going to move this up to the top. So I'm going to pull the 2/3 out front, and then we have the integral of secant squared theta d theta, and hold on one second here. Okay, so we'll have 2/3 secant squared theta d theta, and if we simplify underneath the square root, notice we'll get 4 tangent squared theta plus 4. But I can factor the 4 out front, so I'll still have tangent squared theta plus 1 left over. Okay, and now the trick is, the whole point of doing these trig substitutions is getting rid of the square root. So again, I can write this as 2/3 times of the integral. Still on top, I have my secant squared theta d theta. If I pull the 4 out, it's going to come out as a 2. And remember, there's a trig identity for tangent squared theta plus 1. That's just secant squared theta. So this is the nice thing. Now we have the square root of secant squared theta. Okay, so my 2's will just cancel out, and that'll leave me with 1/3. That'll leave me with 1/3 secant squared theta. And notice if I take the square root of secant squared theta, I just get plain old secant theta d theta. And if we simplify that down, we're just left with 1/3 the integral of secant theta d theta. Alright, so we're almost there now. Last, what we need to do is integrate secant theta, and this is one you may or may not be familiar with. If you integrate secant theta, you get the natural logarithm of secant theta plus tangent theta plus c. The way that you can actually justify that is you multiply top and bottom of this, of secant theta by secant theta plus tangent theta, and then you end up doing a substitution to make this work out. Alright, so now we have integrated. Okay, so we're getting close. The last thing we need to do in this problem is, we started with x's in our problem, but right now we're left with thetas. So we have to somehow get rid of the thetas in this problem. Well, it all comes back to your substitution. So our very first substitution was 3x equals 2 tangent theta. What you do at this point is make a little right triangle based on this information. Okay, so I'm going to make my right triangle. So here's theta. Notice I can solve for tangent theta and get 3x over 2 equals tangent theta. And remember, with right triangles, tangent is opposite over adjacent. You can use Pythagorean theorem to solve for the missing side. So it's this side squared plus this side squared, the square root of it. Well, that'll just give you 9x squared plus 4, which is conveniently the original square root we were trying to get rid of in the first place. Okay, so now I can just plug all of this stuff into my formula here. It says we get 1/3 the natural logarithm secant theta. Well, remember, cosine of theta is adjacent over hypotenuse. So 1 over cosine is secant theta. So that'll give you hypotenuse over adjacent. The hypotenuse being 9x squared plus 4, the adjacent being 2. Tangent theta, again, we could read off from the triangle, but it's right here, it's what we just had. So 3x over 2 plus c, okay? And that'll be your answer to this problem. Okay, so again, a couple typical little tricks here. You've got to know the correct substitution and use the correct identity to get rid of your square root. You'll have to do this little right triangle trick to express your final answer in terms of x's. Kind of long and tedious problems. I think this is pretty, pretty typical run-of-the-mill trigonometric substitution problem. Certainly not easy or mindless, but certainly, again, kind of tricky if you're new to it and haven't been doing a lot of them. So hope this makes sense. Shoot me an email if you got any questions.